great to be here in Singapore with you, and we're very excited to present to you our latest research on the breach attack. So today we're going to show you the latest findings that we have, our latest techniques for extending this attack, and we're going to also show you our tools that we've developed and we're making available today. So first, a few words about who we are. My name is Dionysis. I'm here with my colleague Dimitris. And we are researchers at the Security and Crypto Lab at the University of Athens in Greece. So what we're going to show you today is that HTTPS is broken. And, well, we knew that from Black Hat 2013, but today we're going to show you that, well, we kind of thought we fixed this by switching to block ciphers with AES. But, in fact, AES is also vulnerable. So we'll show you why this is true. And we'll show how you can cryptanalyze HTTPS. So first I want to gauge a little bit of the audience. Who here was or is aware of the breach talk in Black Hat 2013? Raise your hands. Okay, not too many people, so we're going to go through the original Black Hat breach attack real quick, and then we're going to show you our latest findings. So here's the overview of today's talk. First, we will review the original breach attack, and then we will go to our contributions. We will show you some statistical methods of performing this attack, and then we will show you how these can be used to attack both block ciphers and noisy endpoints. And then we will move on to some optimization techniques that we can use to make the attack much faster. And finally, we will present our tool, which is called Rupture. And we will end the presentation with some suggestions for how to mitigate this attack for good. So that's the plan for this next hour. So the original breach research was presented in Black Hat USA 2013 by this gentleman over here, Angelo Prado, with his two colleagues, Neil Harris and Joel Gluck. We're very grateful to you, Angelo, for helping us also with this latest research here. We have based a lot of our work on their paper and their presentation. All right, so how does breach really work? Well, this is a schema that shows how the attack works. We have a victim in the middle, and this is the user browsing the internet on a coffee shop. The attacker has access to the network of the victim and can do various injections and measure things on the network. So this is the attacker, and the victim visits HTTP websites like CNN or Amazon or eBay. And what the attacker can do is they can alter the HTTP responses to include arbitrary JavaScript code. So this is regular HTTP browsing. This is a standard EtherCap or BetterCap alternation of data on the network. And then this code executes on the victim's machine and connects back to the attacker and opens up a command and control channel. And then this command and control channel can be used to make requests to a different endpoint, which we call the target website. For this example, it's Gmail. And this connection is HTTPS. And because of same origin policy, the JavaScript that runs in the CNN context is not able to, of course, read the data, but the attacker can see the data encrypted passing through the network. So this way, we can issue thousands of requests from the browser of the victim. And of course, these requests include authentication cookies. So the response will contain secrets. Right? So this is the basic anatomy of the attack.
Can you hear me?
Yeah.
Okay. So, original breach presented some assumptions in order for the attack to be performed correctly. We will use some of these assumptions, and we will also relax some others. So, first of all, the target website should use HTTPS. And in this case, we don't mind if it also uses HTTPS. The response also should be compressed using gzip. And although the original breach actually attacked websites that used stream ciphers, we will relax this on also to block ciphers. Finally, the response should have zero noise, and most importantly, it should contain a parameter that is actually reflected inside the response. That is, the attacker should be able to inject some plain text of his own into the URL response, into the response. So, the target of the original breach was actually to steal some CSRF tokens And by doing that, the attacker could impersonate the victim client to the server. We will extend this to other secrets as well. So, okay. So, Tai Duong in 2012 in Crime showed that presented the web length leaks. That is, if the plain text of if a plain text is has smaller length, if a plain text A has smaller length than a plain text B, then the encrypted plain text, the encrypted ciphertext corresponding to plain text A, should also have a smaller length than the encrypted ciphertext of plain text B. So, in this case, we actually use this in order to find a secret in the target website. So, let's see what Gmail offers. Google offers a mobile view on Gmail, which can actually use a mobile search functionality, which uses post, but also works on get. So, we can search using get parameters, and actually this parameter that we use is reflected in the response body. And this parameter is also, and this body also includes a CSRF token that actually is valid for all of Gmail. So, we as the attacker can inject our own code, and this, our own plaintext, and this plaintext will be compressed along with a CSRF token for all of Gmail. In this case, we see such a response. Okay, we see such a response. In this case, we have some noise, and the noise is this token here. So this token is randomly generated and per request. So we can control it. We also have our reflection. This here is our search parameter, and also we have the token, which is the secret. So in this case, what is our methodology? In order to perform the attack, the attacker should guess some part of the secret. And in order to do that, he needs to know a prefix of the secret. Well, in this case, Google actually has made our life easier because this prefix right here, the 6 first symbols of the token, are constant across accounts and logins. So you can use it against everyone. So in order to bootstrap the attack, we begin with the known prefix, we extend it, and in this instance we have found some more characters until U4 and until U. And in this case we are testing the next character, which is 4. So in this case 4 is the correct one, and we expect the reflected plain text to be compressed well with the token and to result in smaller compressed ciphertext compared to, say, 5 or 6. So, attack methodology, as we saw, is extending the secret one character at a time by beginning with the known prefix. This results in a complexity of big O n times sigma, where n is the length of the alphabet of the secret, and sigma is the alphabet of the secret. So, what are our contributions? Well, we will extend the breach attack, and we'll show some alternative secrets instead of CSRF tokens that can be actually stolen. We'll attack noisy endpoints, and by noise I mean either some induced noise by the endpoint, like the random token that we showed, or the block cipher, which actually introduces noise in our responses. We'll optimize the attack in order to perform well against these endpoints, and finally we'll propose some mitigation techniques that could actually completely eradicate the attack. So, what are those alternative secrets? Well, actually, anything that is contained in the response plaintext body is a possible secret. So, this is Gmail emails, Facebook chat messages, some financial data, or anything else. So, Facebook has actually used a mitigation technique by masking the CSRF tokens, which is actually good, but it's not enough, because although it prevents the attack against the tokens, it is not working for other secrets in the response body. So, our most important contribution, actually, is the statistical methods that we implement in order to bypass noise. And, Dionysius?
So, okay, what is our statistical method? Well, what we want to do is basically we want to make multiple requests per candidate symbol, and instead of just doing one, and then we want to extract just a mean. And this was also a comment in the original breach work, and the authors are right that it adds a square root of m parameter there, where m is basically the difference between the maximum possible noise and the minimum possible noise. And so we have this extra factor here which makes the attack actually slower. And the reason this works is the law of large numbers. If you take more samples from the same distribution, you see that the variance becomes smaller and it converges to the mean. And the statistical mean converges to the distribution mean. Right. So how do we do this specifically for block ciphers? Well, it's actually quite simple. What we do is we perform 16 requests per candidate symbol instead of just one. And in each of these requests, we pad, we add some padding in the reflection value. And this results in sometimes blocks being aligned. Right? So I'll show it to you in a bit and how this works in a diagram. So we introduce some artificial noise. And that artificial noise is basically just some random characters that are added to the reflection, and this causes the ciphertext to either cross or not cross a boundary. So, okay, this is a bunch of requests that we're doing. So you can see them in the background. I'm not sure if you can see the exact URLs here, but these are the base URLs, and this is the reflection that we're using. I will explain. If you can't see it, it's okay. I will read it. So this is the target endpoint. It's just a PHP URL in this case. And then there is a reflected parameter called ref, and the equal symbol. And then we have the reflection value. And this is exactly what we're searching for example, in Gmail. And here you can see a prefix of the secret that we know. In this case is imper. And then we have the candidate that we're trying, which is A. And so you can see all of these requests contain exactly the same guess. And then we'll fill it up with a Huffman pool, which is exactly the same technique as in the original breach. But the new thing that we're doing here is that we're adding some extra padding here, which is just 5 random characters. So you can see this here. And we call this the block alignment alphabet. And so you can see in the first request we have 0 block alignment, and here we have 1, then 2, up to 15. And so at some point it will reach the block boundary and it will create a new block. So you can see this here. So let's say for example, we know the 5 first characters of the secret, it's secret, and then we're trying to guess if it's T or U or V, right? And the red ones are the wrong ones, and T, of course, the green one is the right one. And you can see we have added here some padding at the end, XY, and you can see that XY was the wrong padding. So this compresses to 15, 16, 16, but because it's encrypted with AES, this is rounded up to 16 exactly. But if we guess the right padding at the end, then this will cause the last byte to spill into a new block. So we can see this on the network. It's 16 new bytes, and this is exactly what's happening there. And this is compressed to, this contains a compressed text of just 1 byte, but it's expanded to 16 by the block cipher. Right. So, noises?
Okay. So, in this case, in our experiments, we used actually 0 noise because we had an endpoint that we could control. So, response body, the plain text response body, actually contained 0 noise. But the problem is that even this is not enough. There are some noises that we can't predict. Such noise can be found in the HTTP header. So the connection field in the HTTP header can either take a value of close or keep alive. In the first case, there are 3 or 4 less bytes. So this would result, HTTP header is not actually compressed with the response body, but it is encrypted. So these 3 more bytes will actually result probably on 1 more block. And we don't like that because it might affect our results. Another case of noise is the actual Huffman coding. So in this case, we can't predict how Huffman tree will be encoded during compression because we don't know the response body, we don't know the plaintext. So even after that, we also introduce our noise for the block alignment. So we don't know how this noise for the block alignment will affect the Huffman tree and consequently the compression and the encryption that we finally see. So there should be more investigation at how Huffman is actually made with gzip, and if we can predict to some extent what the result will be. And finally, another noise problem is the content encoding, which may be chunked. So this would result in the compressed plaintext being chunked, and the boundaries may change per request, and this may affect our results. Okay, so let's move on to some of our optimizations to bypass these problems. We propose here 3 optimizations. The first one is the divide and conquer technique. The second one is the request soup, and the third one is the browser parallelization. Actually, block ciphers of 120 bits, like AES, cause a 16 times slowdown. So these techniques should result in a 500 times speed up, theoretically. What is divide and conquer? So divide and conquer states that instead of issuing the request sequentially, 1 card at a time, we divide the alphabet in 2 halves, the first one and the second one. And we try each half repeatedly. In this case, okay, this is an example. So, yes. We have taken this from our implementation, and you can see here that in the first request, we have the first half of the alphabet, and we have also added the Huffman pool for the second half. And in the second half, in the second request, we have the opposite. In this case, the correct, for each alphabet, we append the testing candidates to the known prefix, in this case, in pair. So in the first case, we try G, F, E, K, J, all at the same time. In the second one, we try the others. The half of the alphabet that contains the correct candidate should result in a minimum min length. So we should be able to see this. And after that, we can continue like that. So we try, at first we have the whole alphabet, then we decide on the correct one, in this case the left, then the right, then the left, and all the way down until we have only one candidate. So this should be the correct one. And what this technique actually does is reduce our complexity from big O n times sigma to big O n times log sigma. So in case we have an alphabet of, say, 64 symbols, like uppercase letters, lowercase letters, digits, and hyphens, this would practically give us a 6 times speed up.
Okay, so this is the divide and conquer technique. Unfortunately, divide and conquer does not always work. It causes a little bit more noisy behavior, and sometimes, to be honest with you, it can cause like the mechanism to work with less probability, right? So in that case, what you can do is you can fall back to the sequential technique and spend more time, but still get results with more certainty. So one strategy could be you try with the divide and conquer technique, and if you don't have a lot of confidence, then you can use the sequential technique. And we can actually extract confidence values by running the attack, measuring running multiple requests per each candidate. So, as we said here, of course, this is not going to be just one request. It's going to be multiple requests because you need the padding, right? So you need to combine this with the padding at the end, the block alignment padding, So you can run multiple samples, you can collect multiple samples, and if the difference in length is quite small, it's maybe less than 1 byte, after collecting multiple samples, then you can say, okay, I'm not very confident about this. My confidence value in bytes is less than 1 byte, and so I will resort to the sequential strategy instead. Right. The other technique that we use to optimize, we call it request soup. This is an interesting technique. It's actually quite simple. And the reason we can do this optimization is because we need to collect multiple samples for the same candidate. So these multiple requests are not adaptive based on each other. They are the exact same candidates, just with different paddings. So we don't really need to measure what is going on in the network in order to decide what to do next. So what we can do is we can use the previous command and control channel, and our attacker can say to the victim, okay, this is the candidate you want to try, and please add the necessary padding of 0 up to 15, and maybe run this 10 times, right? So send 160 requests in batches of 16 for the respective block alignment padding, and all of these can go on the network together. We don't care, because what we want to extract is really just the mean length. So what we do is we send multiple requests from the client at the same time. Then the browser, of course, has specific behavior for this, and we collect the total length of the ciphertext that we measure, and we are unable to tell which response corresponds to which request. They're not necessarily sent sequentially, but we don't really care. We just take the sum of the length, and we just divide it by the total amount of requests that were sent. And this way we can extract the mean among all of our samples. And this actually speeds up the attack quite a bit. So how does the browser do this, right? If you just do the request soup idea, you have the browser put one request behind the other, pipelining them. But if you also take into advantage the browser parallelization, which is our other optimization, you notice that the browser can send up to 6 requests in parallel. Right? So this is a screenshot of how requests go, right? So you have 6 requests running in parallel, and then in the next moment you have 6 more requests running in parallel and 6 more requests running in parallel. So really, we don't differentiate between any of these. We just run all of these together. They're both pipelined and parallelized, and we just measure the whole length. And this is why we call it a soup, because it's just responses coming all together, and we don't tell them apart. We just measure the total length. And because we don't need adaptation, this gives us good results. So what does this mean in terms of time? Well, this is an indication. If we run a batch of 16 requests together, we can do this in 1.5 seconds. And in fact, as you increase the number of requests here, this does not increase really linearly. It increases less than linearly, because there is some overhead in communicating in the command and control channel, and starting up new requests from scratch, etc. So the larger this is, if this goes up by 10, for example, this will go up by less than 10. So it's quite good. If you want to collect more samples, you don't really need proportional time. All right. So today is an important moment for our team. This has been the work of several months for us, and Rupture is what we call our implementation of these ideas. It's implementing all our optimization techniques, it's implementing all our statistical techniques, and it's not a proof of concept, it's complete ready code that you can run on real systems, and we are making it open source right here in Singapore in Black Hat Asia. And we are inviting you to download it and modify it and play with it and try it on your own website and play with different targets and so on. Right? So what is Rupture? Well, it's available right here. Right now, you can go on this URL. It's just been made public by my team back in Greece. And we also have it here in the URL, rupturit.com. You can read also our white paper here, which describes many details of our attack that we cannot just tell you in only 1 hour. And it's MIT licensed. In fact, we keep track of all our bugs and issues in that GitHub repository. And we love pull requests. We would invite you to come in and make changes in our code and try it out. So I want to tell you a little bit about how Rupture is structured and why we made it this way and how it can be used. One thing I want to tell you is that because this attack is quite sophisticated, it's difficult to just make a tool and run it against all endpoints. So if I want to be honest, if you want to run Rupture against an endpoint, you need to study a little bit that endpoint. You need to find, how the secret behaves, what ciphers it uses, how it compresses things, if there is a known prefix, if there is noise, how this noise behaves, etc. And in that case, you need to configure Rupture to make it work. But we're trying to make this process easier. So we call these configuration targets. So you can create a target for the CSRF token of Gmail, for example, or you can create a target for stealing, for example, a Facebook message. And we want to make it as configurable as we can, but because this attack is very ad hoc, right now you will have to modify some code if you want to attack a completely new endpoint that does not behave like an existing endpoint. So we don't really pre-ship it with specific targets on sites like Gmail or Facebook, but we plan to release, to make a sample endpoint on RuptureIt that you can run it on. It's not ready yet, but we will launch it very soon. And we'll introduce a URL here on this HTTPS website that you can experiment with that has zero noise, and so this attack behaves quite quickly, and you can see the bytes being decrypted. And in fact, we'll show you this tool running on a controlled endpoint with limited noise in a few minutes. Right? So this is Rupture. So a little bit about the design of this software. So it's designed to be extensible and modular. We split it up into various components that are completely, or they try to be independent of each other. This is different from the proofs of concepts that we had until now. There was some proof of concept by Angelo and some proof of concepts by us, but they were not really reusable, and writing new experiments with them was quite cumbersome. In our case, we split it up into various components. I will show you the components. And this allows cryptographers to experiment with, for example, the cryptanalysis part without caring about the network part. So, for example, we have a specific module for the strategy of creating new candidates and deciding where the attack will go. And we have a different module for doing the statistical analysis and comparing requests and responses and lengths. And in those cases, for example, cryptographers can say, okay, we don't want to measure the mean, we don't want to compare the mean, give us the ciphertext and we'll do something clever, more clever. Maybe we will use the higher moments in this distribution, and somehow I will find something else, right? So if you're a cryptographer, please go ahead and change these modules to create new analysts that do different comparisons. Maybe you can do something better. Or, for example, the strategy technique, you can swap between the serial technique and the divide and conquer technique, or if you have something else in mind, maybe you can do that, right? Instead of having a binary tree, maybe you can have a ternary tree because, okay, it's faster, but it's also a little bit more accurate, so that's the right balance. So it's made to be configurable and extensible in this way. This is also a general web attack framework. This is interesting. The mechanism I showed you previously, the command and control channel, this is actually something that we do. The Rupture framework deploys a client code that maintains a persistent connection, and this can be used for very many attacks. For example, Crime and Poodle, previous attacks against TLS, could be easily coded in Rupture, and in fact, we have a team of 2 master students that are implementing Crime right now. It's mitigated, but I mean, it's an interesting experiment. So if you want to experiment with new attacks, you can just code them up in Rupture and see how they work out. Finally, we make it scalable. So if you are an attacker and want to attack multiple victims on multiple networks, you can run one Rupture server and deploy multiple clients and then collect data in a central location so that you can analyze it later or compare it across different endpoints and so on and so forth. All right. So this is diagram of our attack. I know it's not very readable, but I will read what it says. So this is similar to the first diagram that I showed you, except it shows how the software components play a role here in realizing each part of the attack. You can find this shape and a better explanation in our paper that you can find on our website. It's much more detailed than what I can say here, so I invite you to download it and read it and give us your feedback. So again, we have one victim here, and the victim is connecting to the web. through HTTP, insecure HTTP on Amazon, eBay, CNN, DeviantArt. And we have this component we call the injector. The injector is just a series of better capped scripts, essentially, that what it does is when it sees an HTTP connection coming through, it puts in some client JavaScript code. And this is the client JavaScript code. This is also our code. It's a different module. The client code is actually quite minimal. We don't do almost anything in this JavaScript portion. This is designed so that it can just receive commands from our server, which is here, the adversarial network, and execute them. So this is actually good for an adversary because if the client receives the malware that we have here, they cannot see really what is going on. So if you develop a smarter attack, the client will not really see what's going on. It will just receive commands and execute them in a dummy way. So this is why we made it this way. So this client here makes the victim perform HTTPS requests to the target. These could also be protected with HSTS, by the way. We don't care. There's no padlock being broken in this attack. The victim doesn't see anything. And we have the sniffer component here, which is written in Python and also collaborates with the injector to perform ARP spoofing. And what this does is it reads data coming in the network, the ciphertext, and simply reports them to the adversarial network. So the idea is that the injector and the sniffer, they could run in a small device on the victim's network, like a Raspberry Pi maybe. It's really tiny. And the attacker, the adversary, can have a more powerful workhorse on their own network that can analyze and do anything that is CPU intensive, and we want it to also be persistent. So this is the adversary, and the adversary maintains these services here. We have one service that we call a real-time service. This is written in JavaScript and Node.js. And what this does is it maintains an open WebSocket connection with the client. So this is the command and control channel. This portion here is not really very clever. What it does is basically keeps the connection open, and then it allows the farther backend to take the decisions on how to move with the attack, what kind of work it sends to the client, and so on. So the real core of our work is here. This Python script is based on Django. And what it does is it has two important components called the strategy and the analyst. The strategy is responsible for driving the attack and taking decisions, dealing with things like divide and conquer or sequential attacks, dealing with things such as the padding, and essentially in the end receiving data from the sniffer and sending what the strategy wants to do. It tells it to the real-time service, which forwards it to the client. We also have the analyst, which does the statistical part of the attack. So what it can do is it compares just two distributions based on samples. So this is completely mathematical, and it's a good place for cryptographers to experiment because they don't have to deal with any of the networking stuff. They just see some samples that have been collected, and then they have to write code that compares things. So they can do smarter things in there. So you can see how we made it modular in this way. And finally, we have a SQLite database where we persistently store the data of the attack. So all the data, all the ciphertext collected are put there, and this can be analyzed again in the future. Of course, this attack is adaptive, but if you want to keep the specific adaptation that we used, you can reanalyze this data in the future with potentially new methods and see if they work the same or not. And if the victim, of course, if the victim network goes down, if the victim shuts down their computer, you still have a persistent, your persistent data right there, and you can keep it outside of the network that can be more unstable. All right, so this was the attack framework there. One nice thing is the persistence of the attack. So this is nice. I think it's not very novel, but I don't think anybody has implemented it in code. I mean, we all know that it was possible, but now it's actually easier. So what I mean by persistence is, well, when the victim opens multiple tabs on their browser, all of them are injected with the malware JavaScript that we have, the client. And this client makes connections back to the real-time service, which keeps open connections with all the open tabs. And what it does is it keeps all the tabs dormant, and it wakes up only one tab at a time, and it tells it to do work, right? To issue requests to the target website. And well, the good part about this is if the user closes that tab, then another tab wakes up and can pick up the attack from where the first tab left off. Or even if the victim closes a browser and opens a new browser, or they reboot their computer and log in back in a few hours, the attack can continue, right? So we have this powerful robustness mechanism where the attack can pick up from where it left off. And because we have this database that keeps the data running, like if the network goes down and comes back up, we can pick up from where we left off. I think this is quite nice. Right, so I already told you about the SQLite portion. And we're now ready to show you how Rupture works in a short demo. So let's take a look at this. Right. So can you zoom in a little bit? I don't think they can see it. Okay, a little bit more maybe? Okay, great. So here is the repository of Rupture. And we have a master script, rupture.sh, and what this does is it basically runs all of the components together so that you don't have to run them on your own. But if you want to distribute them in the way that I said on separate networks, you can totally do that. And now it's cleaning up the old database that we had running, and we have set up the database, and now it has deployed all the various systems on the network, right? So it's running the backend, it's running the sniffer, it's running everything. And now assume the victim visits some URL that can be infected, right? So in this case, we'll just fire up an HTML file that just contains the client script. But imagine this could be any URL and could be a browsing in progress, right? So already you can see there's 16 requests at a time. Boom, 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 right? This is 1.5 seconds. And here you've already seen like 16 completed requests. I don't know if we can zoom in here to see like the URLs. That would be really nice. Right, so this is attacking a controlled endpoint of our part. I'm running it on my personal website. And interestingly, it uses exactly the same ciphers as Gmail and Facebook. It uses AES 128. It uses chunking, and the attack works. Right, so in this case, we're showing a sequential version of the attack. This makes the explanation clearer. And you can see this is the known secret, impair. And we're trying one character, in this case A. And we're adding the pool, the Huffman pool, to achieve a fixed point. And here we have the alignment padding, right? So you can see 0, 1, 2, 3, etc. Maybe I should explain what this is here. This is a part of the URL that is not reflected. We call it an anti-caching parameter. And what this does is basically, if we repeat exactly the same request, because we sometimes have to do that if the result is inconclusive due to noise unrelated to block ciphers, then this will cause the browser to do the request again because we changed it and it's not cached. So that's a small detail there. Here is the backend that's running and outputting stuff. Of course, this is all stored in the database, but it's just also outputting here. And you can see the length that is being leaked on the network. And the number of TLS records that are being recorded, you can see it's actually quite fast. And okay, we have a confidence of 1. This means that we have a difference of 1 byte, and this actually was so this was a byte that was collected. So D is in fact the correct byte in this case, and we have decrypted 1 byte of HTTPS, and this took about 30 seconds for this case.
Well, actually, in this case, you can see that we have collected 2 bytes already, because our known prefix in our control side was impaired. So we have already collected D and I. And if I go a little higher, you can see the time that we... Yes.
Can you also see like the...
right here, yeah. We stole the D character, the first byte, and in the next batch, we stole I, and with a confidence of 1. Where 1 actually... Do you want to?
Yeah, sure. Let's show them the lengths of the various alphabet, right? So each of the alphabet. So you can see here there is one block difference from the next best, right? There's also some noise happening. So there's also another character that probably matched a different part of the plaintext here that also resulted in a slightly shorter length, but this one won in this case. So you can see sometimes there's matching with different parts of the plaintext going on. And you can see the difference is exactly 16 bytes in this case. So one of the things I want to mention is the confidence of 1. This is basically the result of running 16 requests per character, right? So one of them only plays a difference, right? The other ones, because they have the wrong padding and there is no block alignment, they do not play a difference. And another thing I want to show you is there's actually a failed request here. It just happened so in this demo. So yeah, here, reported unsuccessful capture, right? So sometimes the capture doesn't really work, and there's maybe a little bit of, maybe the network doesn't behave as we thought, right? Maybe it sends more TLS records, and when we see something that goes out of the usual in the number of TLS records that we collected or anything like that, we just drop that sample. And in the case where we have a closed tab or something like that by the user, this is exactly what's going to happen, right? So we just throw away the sample set of 16 records that we collected with 16 requests, and we just reissue it in a new tab, right? So this is exactly what's happening here. But in this case, it's not a closed tab. It's maybe something that went wrong on the network, maybe a dropped packet or a TCP retransmission, something like that. So it actually behaved well in this case also. But if we move on to the third byte, you'll see it may require multiple batches to converge to the right character. So maybe running 16 requests per character may not be enough, and it may need to redo it, right? So in this case, you see a confidence of 0, because everything is the same, or not everything is the same, but the top two ones have the same, right? So this is probably a match with a different portion of the plaintext, and by changing the alignment alphabet, maybe we can look at it closer. Okay, and we have a few more slides, I think. Right, so this is the expected runtime. We have maybe 3 minutes per byte because of all the noise that we showed you. But if you use divide and conquer, you can drop it maybe to 30 seconds. This is not as good as the original breach, which broke a whole secret in 30 seconds. But we believe using these persistent techniques, you can stay in the network and keep collecting data and eventually break the secret. It's not unreasonable for a person to stay in Starbucks for an hour or two, and you can easily steal secrets in this case while they browse the internet. And by the way, you can attack multiple targets at the same time using multiple tabs. It doesn't matter, right? You can parallelize these. Okay, so how do we propose to mitigate this attack? Well, in the original breach paper, there were several mitigation techniques proposed, but some of them are good ideas, but we don't think they fundamentally solve the problem. I want to just touch on one of the mitigation techniques mentioned in the original paper, which was quite interesting, which was to separate the secrets from the reflection. And this might work for things like the CSRF tokens. But in case of, for example, Facebook messages, you can use Facebook messages both as a reflection and as a secret. So if your goal is to steal a private Facebook message, what you can do as an attacker is you can add the victim as a friend on Facebook. And to execute this attack, what you do is you keep sending them private messages, and then your own attacker private messages get compressed with the private messages of the victim that you want to steal, with the secret ones, right? So these are secrets that are both secrets and reflections, essentially. And they're very hard to separate. You can't really put them in like different compression contexts without losing the efficiency of your compression. So we think for some things it works, but not for everything. So some techniques that were actually proposed to mitigate CSRF in general work against breach very effectively. One of these is first-party cookies, and this was actually proposed by Mike West in RFC, that is in draft stage. And we are working with him to get it in Chrome 51. In fact, he actually implemented it, and he implemented it to avoid CSRF tokens. But it comes as a very good response to this talk, because once this is implemented, it also mitigates the breach attack completely. So what you do is very simple. When you set your cookie, you opt in to be first party, right? So you write this in your cookie, and now what happens is your cookie is no longer sent in cross-origin requests. And that means that the breach attack, because it is based on only cross-origin requests, no longer works because the responses of the cross-origin requests don't contain any secrets. They're just logged out pages. So this is a very good response to our talk. And on April 8th, actually, Chrome is being released with this feature. So this is really great for the security of the web. We have about 1 week to experiment. Right. So I would recommend if you're a web developer, if you own a web application, or if you are a security consultant for a web application, you can opt in for this. The browsers that don't support it will just ignore it. The browsers that do support it will start taking this into account in a week. And this means that your website will be secure from attacks like breach. So to end, I want to propose some future work. Generally, we welcome patches in Rapture. We think it's a good framework to work on, and we invite you to come and help us develop there. We have many bugs open on GitHub. One very important issue is that we don't have Speedy support, and Google's actually using Speedy heavily. So this means we cannot really attack Google or other websites that use Speedy. But we have very good indicators that our attack would work against Speedy as well. There is no reason why it wouldn't. And then if you help with browser development, if you're a Firefox developer or if you have access to these developers, we urge you to help with first-party cookie implementation. That would be great. And if you're a web application developer, please add this cookie to your website. All right, so the key takeaways of this talk. First, HTTPS with gzip. It's still broken, and it's worse than the previous time. Second, Rapture framework is live, so attackers can use it now. So please take this attack more seriously because it's going to happen in the wild. And do enable first-party cookies on your web app because this really mitigates the attack. And with that, I will end the talk, and thank you very much. And if you have any questions, we'll be very happy to answer them. Okay, any questions? Can you bring the microphone back, please?
Thank you. Good presentation. I have a questions about the future framework. So you mentioned block training. What does it mean, block training?
Rapture.
Block training. Could you back to the future work?
Yes.
And backtracking.
Oh, backtracking. Yes, I didn't mention that. I'm sorry, I skipped that. Thanks for the question. Okay, so what is backtracking is the question. So so the goal of Rapture is essentially to get the whole plaintext, not just one secret. So sometimes, in this case, we even showed you this. When you expand a secret, sometimes there's a match between different portions of the plaintext. So you can get a match on your target secret, but also a match on a different secret. So Rapture doesn't really handle it that well right now. But what we want to do is, and the structure and the module structure of this framework actually allows us quite a lot, is we want to try all the possible paths. In that case, we will decrypt both secrets, right? So what you do is, okay, you know 4 characters, and then you have a list of 24 or 26 candidates, and 2 of them match, right? So you say, okay, we have 2 secrets that match. Maybe both of them are in the plaintext. So you go one path, and you explore, you find out what happened, and then you backtrack, and then you say, okay, I will explore the other path that was also promising. In that case, I can store both secrets that were captured by Rapture. So this is what backtracking means. And we're working on implementing this. We are hoping that it will be on the repository soon.
Thank you.
Actually, I do have a question. So this first-party cookie magic that I was completely unaware of, does it apply to iframes and pop-ups, or only to JavaScript, XHRs, and images? I mean, is it really not sending the session cookie if you create an iframe, or if you open a new pop-up? What are some of the limitations?
I don't know about this. So the question here is, does first-party cookie only involve AJAX requests or image requests, or does it also work for iframes, right? I don't know. You have to read the standard, and I'm also curious about this. We have to take a look. And I'm also curious about the implementation to see if it will correspond to the standard. But I'm hoping it will work for all of these. If it doesn't, maybe we should fix it. Yeah, but it's a good step, I think. Okay, any more questions? There's a question on the back? No? Oh, there.
You mentioned that you think there's... Oh, sorry, thanks. Hi, I'm Darren from the Register, Darren Pauly. You mentioned that you think that this is going to be used in attacks in the wild?
Yes.
Would you say, given, like, considering the complexity of it, how long do you reckon that could possibly take? Like,
you want to take this question?
Sure.
Yes. Okay. So this is actually a nice question because during our research, we were reading an article about the mitigation of crime. So in this article, a professor at Johns Hopkins, a cryptography professor, said that crime is actually not an attack that can be used against you in a coffee shop or Starbucks or something like that. It's an attack that regimes can use in order to track and find dissidents. So I think this more or less applies also to breach. It's a pretty sophisticated attack. It's not easy to implement it and use it against targets like me or you, I hope. But it would be possible for organizations or governments or regimes to use it in order to bypass securities in websites that use HTTPS. So it may not be so dangerous against us, but it is dangerous, and we have to mitigate it.
Right, but I think with the introduction of Rupture, once people start writing target configurations for specific endpoints, it's going to be much easier. So it's lowering like the complexity of the attack quite a bit because the implementation is now ready. So I think it would be good to have this first-party cookie feature in the browsers maybe in the next month. The patch for Chrome is ready, so it's shipping in the next release. We will push for other browser vendors to also do that. I would say if you have a ready target, you don't need too much, right? You need maybe a couple of weeks to maybe target a specific person or...
Yeah, actually, all you have to do is, as Dionysius mentioned, networks are pretty much ad hoc as we attack it. So you have to analyze the network, see the type of requests you take, the type of records you take, and see how you can do this. So at first, we couldn't even attack the noiseless endpoint Dionysius had, and we actually did it in the last week. But if you analyze the requests and see a pattern that emerges from the responses, it is not so difficult to do it, actually. Yes. If the assumptions, of course, are met.
Yeah. Please play with the tool, though. So please run it and see how it works for you. Okay. Any other questions in the audience? Okay, I think that's it. Right. Thank you very much for your time. And if you have any more questions, we'll be here for 2 days.